Okay, everyone, good afternoon. So I've got another quiz up there for you, quiz 6. But this one will cover the new material that I'm going to start today, the control theory material. So you've got 2 weeks to take it. So it's due on the April 3rd. And so in lab, let's see, I assigned the lab 3 in lab last week. Any questions about that? Okay. And we had a quiz due last week, quiz 5, and that's a short one, and I'll just quickly run through it in case anyone has any questions. Quiz 5 was on system Verilog. So the first question, I think it was just 5 questions. The first question said, how many inputs are specified in this module? So there's a clock, reset, load, seed. Those are the inputs, right? Yeah. So 4. 1, 2, 3, 4. And then there's one output. And then the next question, assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 cycles after the reset pulse? So for this one, we are resetting it to 1, 0, 0. So in the first cycle, it's 1, 0, 0. And so the next state, so the way this works is that this always is generating the next state as a function of the current state. So state is used as both an input and an output in here, but the state value is only updated on the positive edge of the clock, assuming that reset is low. So when you reset, and this is an asynchronous reset, so anytime the reset goes high, this will activate, and it'll change the state to 1, 0, 0. On the next edge, assuming that reset is low, so after the reset has, after we stop resetting, the next value of state 2 is 0. So that's going to go to 0. And state 1 will be whatever it was in state 2 previously. So essentially state 1 is kind of like it's shifting down. Whatever the value of state 2 was, it gets shifted to the right by one bit and goes into state 1. So state 2 was previously 1. So we're going to put a 1 into the next state 1. And then the next state 0 will be the OR of the previous state bit 1 and state bit 0, which in this case will be 0 because bits 1 and 0 are 0, 0. Make sense? Okay, so when you get the rising clock edge, the next value of state bits 2 down to 0 will be 0, 1, 0. And then if we take it to the next cycle, you just have to run through this again. Now, state 2 is pretty much always going to be 0 after the cycle after you reset, right? So state 2 is going to be 0 until you reset. State 1 will be whatever the previous value of state 2 was. So you will basically be shifting that 0 down to the right each cycle. And then state 0 will be set to if there was a 1 in either a state 1 or state 0 in the previous cycle. So state 0 is going to be a 1 because it's 1 or 0. Down here it's going to be 1 because it's 1 or 0, right? And so you move down. And then state 1 will have we'll get a 0. We're going to shift this 0 into state 1 and then keep shifting that 0 into that position. So it turns out that the way this is written, essentially if you reset you're going to get 0, 1, 0, and then as you clock it after that you're going to be fixed at this, you're going to end up in this state 0, 0, 1. You'll just stay there. It'll never change. You get locked into 0, 0, 1. Does that make sense? Okay. Okay, give the value of A in the first 3 cycles after reset. This is a very similar question. So A is reset to 1, 0, 1, and then you will, on each cycle, the first thing you do is shift A to the left by 1 bit. Now there's a subtlety here though. Normally if you write code like this, only the second assignment of A would take effect. In fact, that's still what's going to happen. Like only the second cycle of A will be used to generate the next value of A on the clock edge, right? However, this first assignment is a blocking assignment, which means that when you evaluate the second assignment to A, you're going to be using the value that was calculated for A in the first line of code. Now this is kind of uncommon to do this. I'm not sure if I've ever seen anyone write code this way, but this is the way the compiler would interpret it. So basically what you're going to do here is you're going to take this right-hand side of the first assignment statement, and that's going to be kind of a sub-expression that you could use to substitute into the A below it, right? So when you calculate the new value of A, it's going to be shift A to the right by 1, and then XOR it with 111, which flips all the bits. So if you start out with 101, on the next cycle, you're going to shift that 1 bit to the left. So 101 becomes 010, right? If you shift this to the left, you're going to delete the leading one, and you're going to shift in a 0 there, so 010. And then you're going to complement it and make it 101 again. So once again, this is kind of a degenerate code because it really doesn't. A will always be 101. It will just always come out as 101. So it's kind of redundant. Make sense? Because you reset it 101. I'm sorry, 1010, and then I mean that's assuming you reset it. If you don't reset it, then you may get a different outcome. But in this case, because we're resetting it at 101, this code will always produce 101 every cycle. Because you're shifting 1 bit to the left and then complementing all the bits. So 101 shifted left is by 1 bit is 010, and then you complement all the bits, you get 101. Okay, and then what's the problem with the following code? Well, this is using A as both an input and an output. You don't want to do that unless it's in sequential, unless it's clocked, right? But this isn't clocked. This is combinational logic. So this would end up creating a loop, a combinational loop, right? And there's no clock to govern the sequencing of this behavior. So it would continuously increment A as fast as the logic propagation allows. So it would be it would be out of control, right? It would be like an oscillator. Okay. And what are the first 3 values of A generated from the snippet below? So this one starts out at 10101, and in this case you do some bit twiddling here where you take the least significant bit and make it the most significant bit. You duplicate the second least significant bit twice. You complement bit 3, and then you add bit 2 XOR bit 4. So the only way to do this is to build a table. And so you build the table as before where each row is a cycle. And so you're calculating you've got the current value, and then you have the next value. The next value is generated as a function of the current value, and then this next value then gets carried down to the next row on the next cycle, right? Okay, yeah, if you're comfortable with that, I mean that's then that's a big part of Verilog design, is understanding how that clocked logic works. Okay, so the next topic, we're going to switch gears quite dramatically and talk about control theory. I don't know if any of you heard of control theory. They teach a course on control theory in the electrical engineering department, electrical 331, and in the mechanical engineering department. This version will just be an intro. So this is just a basic. I mean, obviously, because I'm only going to spend 2 lectures on it. So I'm going to start out with a rant about toasters and washing machines. So a toaster, you know, I don't know if you have this issue, but like if you like your toast a certain color, you know, a certain toastiness, right? You know, the toaster has a setting where, you know, presumably you can set the control on the toaster. So you have this idea in your head of what you want the toast to look like, and then you have this process in your mind where you're going to translate that into a setting on the toaster, and then you activate the toaster, and then the toast comes out. And in my case, it's never right. It's always either too cooked or not enough. And it kind of, this is an example of what's called an open loop control system, where you have some desire, you have some set point that you have in mind, and then you control something, and then you get an output, and then you just hope that the output is what you wanted. The same thing with clothes dryers. Clothes dryers, in my experience, no matter what setting you put on the clothes dryer, I almost always get damp clothes out. I don't get what I want, which is dry clothes out. So the problem here is that neither one of these devices have any way to evaluate the quality of the output and then compare that against what you want for the input, right? They don't have this in toasters. Like they could have like a sensor inside the toaster that senses how brown the toast is, and then they can compare that to how brown you want it to be, right? And then it would, once it reaches that desired level of brownness, it would eject the toast. Same thing with the dryer. You know, there could be a humidity sensor in there, measure that, but they generally don't have that in there. The alternative approach is, you know, like I said, is this closed loop system where the toaster can somehow compare what the toast currently is to what you want, and then it would feed the difference between those two values as an error signal into some kind of controller, which then would control the temperature of the toaster, or whether, you know, it's time to turn it off, right? So that's called a closed loop control. So in control theory, these are the basic parts. They have some kind of a controller, and then they have something you're controlling. And the thing you're controlling is usually called the plant. And that's because I think when controllers first were developed, they were developed for plants, like factories, right, to control factories. Although I always thought that like an autopilot system for an airplane might have been one of the first, or for a ship, first kind of controllers. But anyway, the terminology is plant. So you have something that you're controlling, and then you have a controller, right? And then the plant is going to have something that you can sense or read for the controller. The controller has to be able to have observable variables from the plant. Now, not all variables are observable. Some of them are internal that you can't see. Some of them are hidden. But the ones that are observable are called process variables. So the plant is sending process variables back to the controller. So in the case of the toaster example, the process variable would be like the brownness of the toast, the color of the toast. And then there's a signal that goes from the controller to the plant, which is the input to the plant. That's the manipulated variable. It's like, for example, the control signal. Like for a toaster, it would be like kind of how hot to make the toaster, or whether to have it on or off. Now the problem with this is that you also have another input into the plant. You have disturbances. So you have things that you can't account for in the environment. So the objective of control theory is to be able to develop a controller that will read in process variables and output manipulated variables in a way where the plant will reach a desired set point. So you want the plant to do something, and the plant could be a motor, or a voltage converter, or an amplifier, or servo. It could be a battery, but in every case you have something you want it to do, or some state you want it to reach, and you want to get there. You want to get it there as quickly as you can, which is kind of the main performance criteria of a controller, is what's called rise time, which is how fast it takes to get to the set point. But if you go too fast, you risk overshooting the set point. So if you're charging a battery, for instance, you don't want to overcharge it. You want it to get it up to charge as fast as possible, but you don't want to overcharge it, right? Or if you're controlling a speed cruise control system in a car, you want to get to the desired speed as quickly as you can, but you don't want to overshoot it, or at least not much. But you're also doing this in lieu of these disturbances, which are affecting the plant from its environment that you can't necessarily account for. So if you're controlling a drone, this would be like if the drone gets hit by a gust of wind, or you have some unmodeled, unpredictable forces acting on the plant. And so a controller hopefully will be robust against disturbances as well. So control systems, I mean, you may not realize it, but there's a lot of things. All these cyber physical systems are control systems. Obviously, a self-driving car has a lot of controllers in it. It's controlling the motors and the speed and staying inside the lane, that kind of stuff. Cameras actually have control systems in their focusing mechanism. So they focus, but they want to reach the set point where they're in focus, but they ultimately have to control motors for that. So these are both pretty high speed controllers. A thermostat would be a kind of a lower speed one. You want to reach a certain temperature, and you don't want to overshoot it. And then of course a drone has to fly itself and has to reach set points as determined by its flight plan, basically. And also, one thing you may not realize is that there's controllers kind of built in that are not as obvious. Like in a Tesla, you've got a bunch of controllers in here that regulate the voltages, and then, of course, if like a printer or robots, have a lot of controllers in them that are controlling various aspects. And this is my favorite one, the hoverboard. I didn't realize that hoverboards had controllers in them until I bought my daughter one for Christmas one year, and she was using it, and then she was scooting around with it, and then the battery died, and it pretty much just threw her off instantly. And the reason, and I didn't realize this, but there was actually a controller in there that was actively keeping her balanced on that thing. Well, when the battery died and the controller lost power, it couldn't control it anymore. So she couldn't stand on it at all without that thing actively balancing her. And by the way, that hoverboard is basically the same principle as this inverted pendulum robot, basically a robot that keeps itself balanced. I've been wanting to build one of those for a long time. Okay, so with control theory, there's, it's obviously, the problem with control theory is a lot of it is theory. So if you take Electrical Engineering 331, it's called control theory, but you don't build any controllers in that class. You just do math. It's a math class. There's no practical side of that class at all, as far as I know. Now, they do have one though, the Electrical Lab 301, I think it is. They actually control like a race car. That one is the applied control theory class. The one in mechanical engineering is a little bit more applied. Yes.
You talking about the
race car, yeah. Did you take it? Oh, did you like it?
Pretty good.
I heard it's difficult. Yeah, so that's like their applied theory, control theory class. Excuse me. In this class, I'm covering control theory because I wanted to introduce the effect of computing on control theory. So there's some issues there when it comes to when you design a digital controller, you have to discretize time. You have this time step, and when you have a time step in a digital controller, there's a certain amount of time you have to calculate your control decisions. And if your CPU isn't fast enough, or if your code isn't optimal enough to achieve that performance constraint, that execution time limit, then the system can fail. Likewise, with a digital controller, like the ones that we will do in the next lab, you have to worry about interfacing too. So you have to worry about computing and interfacing and protocols. So there is a computing aspect to this, to the practical side of control theory. But just to kind of quickly cover the theory of it, there's a couple different ways that you can conceptualize control systems. The simplest way is through this thing called a linear time invariant system. So what is a system? A system is a collection of components, and an LTI is a way to describe a system as a linear differential equation. So when you hear linear, like, when I hear linear, what do you think of? You think a linear system is a system in which you have variables that are just multiplied by constants, right, and added, right? You can't like take variables and say square them, for instance. That would make it nonlinear, right? But then if you say linear differential equation, then you're like, well, wait a minute, differential equations are not linear. Like if you plotted a differential equation, it would not be linear. It would have a curve to it, right? So how can you have a linear differential equation? Well, what that means is it's a slightly altered definition of what linear is. An LTI is a system where it's an equation where you have variables. Those variables are time series variables. So it's like they're signals, like x of t, right? So they're variables that change with time. And then those variables, those signals, can be differentiated, right? Or they can be integrated, right? And additionally, you can differentiate them or integrate them or not, or just have the basic signal. Like, so you can have x of t, or the derivative of x of t, or the integral of x of t. And then you can then multiply any of those things with a constant and add them up. And that's it. That's all you're allowed to do. So as long as you treat the time series variables as a variable in a linear system, and you can also have the derivatives or integrals of those variables, that's fine. And you can multiply them by a constant, and you can add them up. That's it. If you obey those rules, then you have a linear differential equation. Okay, so a lot of control theory, at least basic control theory, is based around these linear differential systems, LTIs, linear time invariant systems. So in other words, linear means that you can't have state terms. State terms are variables, or the derivative of variables, or the integral of variables. They can't be multiplied against one another. So that's what the linear means. And the time invariant means is that the coefficients that you multiply against those variables have to be constants. They can't be time series coefficients. You can't have coefficients that change with time. You can just have coefficients that are constants. Okay? So LTIs have a frequency response that allow you to have an input and an output where the output can change the phase and amplitude of an input, but it can't change its frequency. It's not something you do with a linear or an LTI. So it's kind of like, if you have a circuit that just has RLC circuit, right? In circuits, if you remember from electrical 221. Okay, and then the output signal, if you're looking at it as like an input, having an input and an output. Now, by the way, a differential equation doesn't necessarily have inputs or outputs. it just has these state variables, right? But when you build a model of a plant or a controller, then you're going to pick out some of these as inputs and some of these as outputs, right? And so if you conceptualize it like that, you can come up with something called a transfer function, which is a function that's built as an LTI that allow you to see how the output function is a changed form of the input signal, or the output signal is being transformed from the input signal. Okay, so let me give you an example. So a simple example would be this system where I've got two signals, U and Y. And this is just an equation, so I just happen to have U on one side and Y on the other side of the equation. But of course, you don't have to have it like that. And then U and Y, these are both signals. They're both changing with time. They're time series signals. And over here, I've got the derivative of Y with respect to t and the integral of Y with respect to t. And in this case, I multiply the integral by -6 and then, add everything together. So this is a linear system. This is an LTI system. And you can have more than one, you could have more than two signals in there. In this case, I just have two because I'm going to use this as a single input, single output LTI. So this, you could say this describes the dynamics of signals Y and U. And normally, to simplify this, you would represent this in the S domain, the Laplace domain. And this is pretty simple to do because if you have, for example, U of t, the Laplace of that is just U of S, right? But it's usually capitalized U. If you have the derivative of a signal, so in this case, the derivative of Y with respect to t is just rewritten in the Laplace domain as having a coefficient of S, S capital Y S. And then the integral of Y sub t, if we bring that into the Laplace domain, it becomes, the first integral is S 1 over S, or S to the -1 power, right? And then that coefficient there, 6, that -6 there, just comes straight across into the Laplace domain, right? So basically all you have to do when you do the Laplace transform of this is that you capitalize the signal names. Instead of them being a function of time, they're a function of S. And then derivatives become S, or the second derivative is S squared, and the third derivative is S cubed. And integrals are essentially 1 over S for the first derivative, 1 over S squared for the second derivative, and so on. Okay, so I'm sure you guys covered this in circuits, right? Okay, so when you're in the Laplace, excuse me, when you're in the Laplace domain, the S domain, the frequency domain, you can build your transfer functions. You basically have to decide what's your input and what's your output. Okay, so in this case, when I had it in the time domain, it was pretty obvious that Y was the input here and U was the output. When I get it in the S domain, you can construct a transfer function in which the input is in the denominator, is in the denominator, and the input is in the numerator. And by which I mean that all of the all the terms that are inputs that are with respect to the input, in this case U, are in the denominator. And the reason they're in, and of course all the outputs are in the numerator, right? So what you end up with here is that your goal is to essentially get a ratio of two polynomials of S to construct the transfer function. So in this case, in order to get this transfer function, I have to do a little work here. I have to go over, so the left-hand side, I don't have to do much, right? I leave that alone for now. If you look at the right-hand side of this equation, if I factor out Y of S, right? So I factor out Y of S, I get y of s times 1 plus s minus 6s to the minus first power. So basically, I'm going to factor out y of s because then I can divide both sides by y of s, and I end up with the, on the left-hand side, I end up with that ratio y of s over u of s, and I end up with this 2 ratio of polynomials where I've got 1 over 1 plus s minus 6xs to the minus first power. Make sense? And so this becomes the, now you might say, wait a second though, like, can I have y as the input and u as the output? Yeah, that's no problem. If you wanted that, you would just invert. You just flip, if you flip the numerator and the denominator, you end up with a transfer function where you're treating y as the input and u as the output, right? But I'm doing it this way just because in this system, that's how I'm modeling the system where y is the input and u is the output. Or sorry, u is the input and y is the output. Right? Is that right? Y is the output. Yeah, that's right. That's right. Yeah, actually, I misspoke. Actually, if you look at the time series one, it almost looks like in this case, the way this is written, that u is the output, right? Because u of t is by itself. But in reality, or well, like I said, that can be the output. But in this case, we have y as the output and u as the input. Does that make sense? So it's sort of this time series. The way I had this one structured, it sort of implied that u is the output, when in fact u is down here, as I made a u the input and y the output. Okay, so now in addition to controlling a plant, an important thing you want to, an important objective you have with a control system is stability, because a lot of plants, if you take a plant and you try to control the plant with an open loop controller, like the toaster example I talked about earlier. Toasters are open loop, right? Some systems, if you try to control them with open loop, they can't be controlled at all because they're unstable. They're inherently unstable, meaning that if you try to do an open loop control of a plant, there's no guarantee that the operating state of that plant won't destabilize in the sense that its magnitude grows and grows and grows ad infinitum. Now, obviously, in reality, there's a limited amount of energy, so it won't go to infinity, but things will fall apart. And an example of this is the F-16 fighter. The control surfaces on an F-16 fighter are unstable. So the pilot actually doesn't control the airplane directly. The pilot's commands go into a computer, and they form the set point. They provide the set point for the computer, and then the computer has a controller that's constantly making control decisions to stabilize the plane. So in other words, what I mean by that is that if you have an unstable system, you can combine the unstable system with a controller in a feedback loop, in a closed loop control, and that resulting system will be stable from the perspective of the input into the control system, the set point input, because this input is a set point, right? So you've got an input. The terminology is a little weird because the system has an input. So the controller generates an input to the system. The controller has an input as well, but that's not the same type of input. This is a set point, and this is a manipulated variable. And then you have this signal coming back from the system back in the controller, and that's the process variable. So you have the manipulated variable here and the process variable here, but then the top level input, this is kind of from the user's perspective, this is a set point. And so if you combine the unstable system with the controller for the purpose of stabilizing it, you end up with two transfer functions that you put together, that you connect in series, and then that whole system can then be stabilized. So, and that's what's happening here, is that it's stable from the sense that I can put a set point in here, and I don't have to worry about the system blowing up. This is called bounded input, bounded output stability, meaning as long as I give it a bounded input, then I'm guaranteed to have a bounded output. The output won't go infinite. So the question is, and this is where the theoretical part of this comes into play, how can we determine if a system is stable? So I mean, each one of these blocks is a system, but then if we combine them, we just have a bigger system, right? It's kind of like Verilog, where you can have modules, and you can combine the modules to make bigger modules, more abstract modules. One way to understand the behavior of, now in Verilog, the behavior is defined in Verilog, obviously. In one way in control theory to look at the behavior of these is as an LTI, assuming they're linear systems. So, or they can be viewed as, in reality, nothing is linear in real life. I mean, nothing is really linear. Like one example they usually use in control theory is a spring. Like a spring is, you can think of that as a linear system, but the farther you pull a spring apart, the more force it exerts to pull back in, right? But the problem is that, and that part is linear, but if you keep stretching a spring out enough, it'll just break, right? And that's a nonlinearity. A resistor, for instance, most people think of resistors as linear devices, right? They just follow the resistances, they follow Ohm's law, right? And the resistance is constant, right? Because you go and you buy a resistor, it has a constant resistance. It turns out it actually doesn't. Any resistor actually has a changing resistance. The more current you pass through it, the hotter it'll get, and the hotter it'll get, it changes the resistance value. So it's mostly linear, but not exactly linear. But a lot of these things we want to model as linear systems. So if you're modeling these as linear systems, then you can associate an LTI, which is a linear differential equation, or a transfer function. You can associate this with each block, and then you connect the blocks together, right? So if you have one LTI, question is, how do I know if it's stable or not? And likewise, if I have two LTIs connected in this feedback, how do I know if the resulting closed loop feedback system is stable, right? That's the question. Okay, so there's several ways to determine that. So one of the ways that's very common is to use is to look at the impulse response. So if you have a system in LTI, you can hit it with an impulse and see how it responds. If the system is unstable, then it will blow up in response to the impulse. Now, first of all, what's an impulse? An impulse is a function that at time 0, it's infinity or 1. And at every other time, it's 0. So it's basically a pulse. You can think of it like a reset pulse, like when you reset a Verilog module, except it has infinitely short duration, right? It's only non-zero at time 0. The other option is to use a step response, where instead of an impulse, you can use a step where at time 0, it's 1, and then at some time after that, it goes to 0 and then just stays there, right? Just like kind of like a clock signal, duty cycle on a clock, right? Now, what's the significance of the impulse in the step function? Why would you use those? What's the point? It's because in order to create either an impulse or a step by adding together sinusoids, you would have to add an infinite number of sinusoids in order to create that impulse or that step, right? And the reason is because the step has a very sharp edge that goes straight from 1 to 0, right? And when it comes to systems that are unstable, Generally speaking, they're not unstable for any input. They're only unstable under certain frequencies of input. And so by doing an impulse or a step, you're essentially exposing your system that you're testing to an infinite number of frequencies, like every frequency, right? And so if it is unstable in response to any frequency, then it is guaranteed to become unstable after having experienced an impulse or a step, right? Another approach, though, is to use, if you have the S-domain transfer function for the whole system, you can find what are called poles. Poles are, now remember that the S-domain transfer function, as I showed you, is a ratio of two polynomials, right? There's a numerator polynomial and a denominator polynomial, right? Both are polynomials of S, right? The poles are values of S in which it'll make the denominator 0, so you'll end up with a divide by 0. Those are poles. Now S represents a complex number. So these are complex values, right? There's a real and imaginary part. But if you find the poles, all the values of S that will create a divide by 0 in the transfer function, if all of those poles have a real component that is less than 0, negative. If it has a negative real component, then that means that all of the poles, the values of S that create a divide by 0 are the poles. All the poles are what they say are in the right-hand plane, meaning if you look at just a plot of all those poles, they're all to the left of the 0, x equals 0. Make sense? Okay, I'll show you an example of what I was saying. But if they're all there, that means it's stable. And then a third option is you can simulate with a step or a sinusoidal input. You might say, what's the difference between 1 and 3? 1 is where you're looking for the impulse response, calculating it, and 3 is where you actually simulate the response. Now we're not going to learn any simulators for this. I mean, there's actually not a lot of options for simulating it. I think the most common way is to use MATLAB. You can use MATLAB to do a simulation of one of these systems. In this class, we're just going to look at options 1 and 2. Okay, so here's an example here of this is the impulse function. This is also called the Dirac delta. So it's basically at time 0 you pulse it, and every other time it's 0. And then the step function looks like this. We have 0, 0, 0, 0, 0. At time 0 it goes to 1. And then it stays, oh, that's right, it just stays at 1, right? You don't have to necessarily return back to 0. It's just a pulse from 0 to 1. You guys with me? Okay, so, all right, so what about the example that we looked at then? So this was the example, was this the same example? Yeah, this is the same example we looked at before. So this is a transfer function, and again, this is okay, so let me clarify this. So when you're looking for poles, the poles are found for the transfer function. Obviously, those poles are going to change if I use U as the output and Y as the input, right? So in order to figure out what values of S will make the denominator 0, it's important to know what's in the denominator, which is determined ultimately by what we consider the input and the output of the transfer function to be. Okay, so we're looking for poles specifically for the transfer function where U is the input and Y is the output. And so in that case, our transfer function is 1 over 1 plus S minus 6S to the minus 1. And so the objective here is to find what values of S will give you as divided by 0 here. Okay, so how do we figure that out? How do you figure that out? Well, I don't know how to do that unless I can take this polynomial and factor it, right? And I don't know how to factor it in that form. But if you multiply the whole thing by s over s, so if I multiply this by times s over s, if I multiply the numerator by s and I multiply the denominator by s, now this denominator becomes s plus s squared minus 6, or actually, which to reorder it is s squared plus s minus 6, right? I actually get a polynomial that you can then factor. So I can factor that into s plus 3 times s minus 2, right? And so in this case, there are two values of s that will give me a 0, right? -3 and +2. So those are the two poles. Now, again, these are imaginary numbers, s, but in this case, the poles only have a real component. So if you look at this plot where the imaginary component is the y-axis and the real component is the x-axis, you can label those two poles on this plot. And as long as all the poles are to the left of the x equals 0, meaning that they're all negative real. The real component is negative, meaning they're in the left-hand side of this plot. Then the system is stable. The problem is that this is not a stable system because I got this guy over here, right? Now, it doesn't, but as I mentioned earlier, this system may be stable for some frequencies, but not for others, right? All this means is it's not guaranteed to be stable under any input. For example, the impulse or the step. Put an impulse or a step which contains all the frequencies, and this thing will blow up. However, if I'm putting a sinusoidal input in, there are certain frequencies I can give it where it'll be okay, but other ones I can give it that'll be bad, right? So this is an unstable system because the poles are at -3 and 2, and that 2 pole is the issue. Now, another way to look at this is to take the transfer function and convert it back to time domain from S domain. Go back to time domain. Right? Now remember, we started out with the time domain function, right? Or we started out with a time domain differential equation, right? And then we kind of rearranged it a little bit, or no, we did the Laplace transform on it. And then we rearranged it a bit to create a transfer function, right? But you can, if you want to go now from this back to time domain, how do you do it? Well, it's pretty hard actually to do that. So the one way to do it is to look at a table. This is generally what people do. They look at a table where you have one column of the table is the time domain and the other column is the S domain equivalent. But those tables are actually kind of hard to read. But luckily, there's really only one entry that matters for us because these are linear. We're working in a restricted space of Laplace functions. So the one entry in this table that's interesting here is relevant to us rather, is 1 over S minus A translates to the time domain version of that of e to the negative at, right? So if we can get this equation into this form, we can then transfer it directly to the time domain as an exponential. Does it make sense? Right? So the goal is, can we get this in this form? And we can. Well, sometimes we can. It depends. You'll notice here that this polynomial s squared plus s minus 6, it has two roots. It's a second order polynomial, and it has two roots, two unique roots, right? Which is good for us, because if you have a unique root, if you have unique roots, then you can use this trick, this little algebra trick. So s over s plus 3 times s minus 2, we want to figure out how we can reform that into something over s plus 3 plus something over s minus 2. Have you guys ever done this before? You want to break apart the denominator, right? The problem is that this doesn't always, like I said, this only will work if you have unique roots. I don't know how to do it if you do. I think there is a way to do it if you don't have unique roots, but this is the easier way to do it is if you have unique roots. You can use this method. So the question is, we want to figure out what a and b are, because if we can figure out a and b, then we have this sum of these two expressions that are both in this form. And then we can go straight to time domain, and the time domain version of that is an exponential, right? This is also called an eigenfunction. This thing. You guys with me? The problem is that how do you do that? I mean, there's two unknowns and there's only one equation. Seems like it's an underdetermined system. How do you find two unknowns with one equation? A and B, the unknowns here. Well, there is a way you can do it. So if you take this guy, a over s plus 3, right, and you multiply that times s minus 2 over s minus 2. Just this part. So you take this guy and you multiply it by s over 2 times s over 2. You're going to end up with a times s minus 2 over s plus 3 times s minus 2, right? Likewise, on this side, this guy, you can multiply this fraction, this sub-expression, by s plus 3 over s plus 3. So that will give you b times s plus 3 over s plus 3 times s minus 2. So you end up with a common, when you do that, you end up with a common denominator, right? And it matches the common denominator, the denominator that you already had on the other side of the equation, right? So the idea is that this is where you start, and you want to create a common denominator of s plus 3 times s minus 2 on the right-hand side, right? So to do that, you just multiply each one of these by 1, where the 1 is, again, is s over 2 over s over 2 on this side, and s plus 3 over s plus 3 on this side, right? So you end up with this, right? So, I mean, the problem, though, is that we still have two unknowns in one equation. So that doesn't really help much, except now we can factor out the denominator on both sides. So now we end up with just s equals a times s minus 2 plus b times s plus 3. Okay, it's still one equation and two unknowns. So how do we deal with that? Well, we can assume that we can consider the case where s equals 2. Because if s equals 2, if s is 2, it'll make this sub-expression 0. So it'll knock out the a unknown. And we'll just be left with the b side with the value of s, which will be 2, right? So we set s to 2. If you set s to 2, then you end up with an equation where s has been assigned to 2. The a sub-expression gets zeroed out, and we end up with just one unknown in one equation. We end up with 2 equals b times, it was s plus 3, but now it's going to be 2 plus 3. So you end up with 2 equals 5b, right? And likewise, we can set s to be negative 3, which knocks out the b variable, and sets s to minus 3. So you end up with minus 3 equals a times minus 3 minus 2, right? And so we have these two equations now, and we have two unknowns, right, a and b. And now we can figure out, okay, solve for a and b. And so what you end up with is a is 3/5 and b is 2/5. So you end up with 3/5 over s plus 3 plus 2/5 over s minus 1. So I solved for a and b, and then I went back to the original equation and plugged in those values. So you end up with the form that comes from the table. So I can calculate the time series, the time domain version of this. I could do the inverse Laplace transform, and I end up with essentially, I end up with this as my transfer function. So this is what, this was 3/5 and 2/5. And then, so I do the inverse Laplace there, and I end up getting, just using that table, just going from here to here, a is 3 over here, a is negative 2 here. So I end up with 0.6 e, because the 0.6 is my coefficient, e to the negative 3t, right, plus 0.4 e to the 2t power. You guys see that? So the time domain version is this. The problem is that this part is the problem. I have this 2t, which means that as time advances, oh, and by the way, one thing I want to mention here is that the one thing I forgot to mention here is that the this is the time domain inverse Laplace transform of the transfer function that is formed from hitting the system with an impulse. You guys with me? What do I mean by that? Okay, so if you have the reason why people use the impulse response as opposed to the step response, or as opposed to a sinusoidal response. And when I say response, I mean, let me back up here a minute again. The response is you have to have an input and an output, right? When you calculate a response, you're calculating how the input responds to an input. I'm sorry, how the output responds to an input. If you do the inverse Laplace transform of a transfer function, that gives you, for free, the impulse response, the response to an impulse. And the reason I say that is, why am I saying that? Because notice there's no input here at all. This function, 0.6 times e to the negative 3t, is a function just of time. There's no input, right? So this is this represents the time domain response, assuming I've put an impulse in. Now the problem is, you might say, okay, but what if I want a step response? What do I do then? Well, then you have to do more work, right? The impulse response is given to you for free by simply calculating the inverse Laplace transform of the transfer function, just the raw transfer function, okay? So, so if I plot this, what ends up happening is, if I plot this with respect to time, the system, well, by 10 seconds, it blows up, right? So we're fine for, for 8 seconds, we're good, but then it just it diverges there, right? It very quickly ramps up and diverges. So that is the, represents the impulse response. Now, if I want to do the step response, there is a mathematical way to do it. However, instead of doing that, I'm going to take the easy way out, and I'm just going to simulate it. So this is I generated these plots with MATLAB, and so I created a Simulink design where I have a step, which looks like that, right? That's the step. So time, actually, it's not exactly well, it's a step, but it doesn't step at 0, it steps at 1. So time 0 to 1, it's 0. Time 1 and on, it's going to go to 1. Okay, you see that? There's a step. If I hit this LTI transfer function with this step, you can see what happens is it's kind of weird. I don't really, it starts to kind of wiggle and oscillate, but then it just keeps building and building and building, and it blows up. So you might say, well, that doesn't look like the kind of the straight ramp up we had with the impulse response. Yeah, but I mean it's a different response. It's still going to reveal that this is the output is not bounded, right? But the output you see in response to a step is slightly different from the output you see if you give it an impulse. Does that make sense? Right? They both serve the same purpose, but the actual response is different depending on if you give it an impulse or a step. Okay, now here's another example. I said, well, if I'm going to simulate, I might as well hit it with some other stuff. So what happens if I simulate it with a sine wave, sine 2t? Now, if you say sine 2t, that is a frequency of 2 radians per second. 2 radians per second, as opposed to cycles per second. So you can see that's the input now, and the output it blows up. So it is possible to hit this with a frequency that doesn't cause it to blow up, but the one that I picked, 2 radians per second, does make it blow up. But you can't. This is a little harder to figure out to solve it for on paper. That's why I just simulated it. Okay, well, what if we have a system that is stable? Okay, so let's just take the existing system we had, and I'm going to force the thing to be stable. The way I'm going to force it is I'm going to change the polynomial so the denominator is now factored as s plus 3 times s plus 2. So the roots here obviously are -3 and -2. That's what the poles are. And because both poles have a negative real component, this is definitely a stable system. Okay? So if I go through the same math again, so now I have to solve for a plus b. Again, I'm calculating this impulse response by finding the eigenfunctions, which is the inverse Laplace transform. I have to go through the same steps I did before. So I have to calculate a and b, which are the numerators of each of the 2 components. And it turns out that the numerators here are -2 and 3. Make sense? And then, so the inverse Laplace transform is the 2 and 3 just become coefficients to the exponentials. And the exponents are -3 times t and -2 times t. So your poles are essentially just the coefficient that's multiplied by t in the exponents. And when you plot this, you can see that you give it the impulse, and you can see that it goes to 1, and then it comes down to 0, and then it just kind of stabilizes, right? So this is how that system would respond to an impulse in the time domain. So I simulated this too in MATLAB. I hit it with a step function, and you can see, there's no weird oscillations anymore somehow. You hit it with the step, and it kind of goes up, and then it kind of comes down and decays. Where'd the oscillations go? Still an LTI, but there's no oscillations anymore. It looks as a better response. If I hit it with sine 2t, 2 radians per second sine wave, it just, well, I get a sine wave out. Notice that the magnitude has changed, right? Because I gave it a amplitude here of 1, and on the output it's 0.2. But the phase and the frequency didn't change. The frequency can't change. The phase could have, but the phase didn't because the poles didn't have an imaginary component. Are everyone with me so far? Does that make sense? Okay, so now I mentioned these transfer functions, and I also mentioned that you can build systems. I haven't really talked much about that yet. So the transfer functions are these like ratios, right? Output divided by input in the S domain. So we have to have an input and an output. We have to choose our input and output, right? So the LTI just describes the dynamics, but if we conceptualize them as a transfer function, we have to pick inputs and outputs. But the cool thing about it is, if you have two transfer functions where one feeds into another, all you have to do to calculate the overall transfer function of the pair is to simply multiply the two transfer functions together, right? Which makes sense, because if I'm going to call this y and this is g, and these are usually named after their outputs. So this is y, this guy is y over u. And this guy is g over y. And I want to calculate g over u, right? So I just multiply y over u, this guy, y over u, multiplied by g over y, and I end up with g over u. So this works out mathematically, because the y of s just cancels out. Right? This guy cancels out, right? But it turns out that if these are transfer functions, you do the same math, and you calculate a new transfer function for the whole system. That's kind of cool. It just requires algebra essentially. Now, you might say, well, wait, hold on. That's what is that though? I mean, what are you building there? I mean, there's no feedback there yet. No, I haven't put the feedback connection in. So this is an open loop controller so far. I've got a plant and I got a controller. The controller is driving the plant. There's no feedback yet. I haven't put that in. That takes a little bit more effort. But all I got to do to then create a model of the whole system is to just multiply those two transfer functions. This is called a convolution operation when you do that. Okay, so let me give you a quick example of a practical application of this. This is really simple. Should probably have a better, but let's just a better example. This is a really simple example where let's assume for a minute. Do I have a picture of this? Yeah. So let's assume for a minute that we have a physical system, not an electrical system, but a physical system, in which I have an object. Think of it like like a coin, and I want to be able to push. I want to apply a force to the coin, and my goal is to have it push it to a certain distance, which I'll have a set point there for that. Okay, so U is the force I want to apply to the coin, and Y is the distance I'm going to push it. Make sense? And I'm also going to have some parameters here. I'm going to assume the coin has a mass of m, and I'm going to assume that there's a coefficient of friction between the thing I'm moving and whatever it's sitting on. Okay, so real simple physics a setup here. So one way to write this in the time domain is U is the force I'm pushing on it. There's also a counterforce that comes from the friction. The counterforce is the coefficient of friction multiplied by the speed at which it's moving. the speed it's moving is the derivative of y, the derivative of the distance. Now, in this case, instead of using d of y over d of t, I just say y dot. That's a shorthand for the first derivative. Make sense? Dot. You might say, well, okay, well then what's the shorthand of an integral? I don't know. There's only shorthand for derivative. I don't know how you do integral with this notation. So as long as you got derivatives, use a dot. Okay, and that is going to be equal to, that's the total force, right, that's being applied. So I have to, that's going to be equal to the mass of the coin times the acceleration, which is y dot dot. That's the change, the second derivative of the distance is the acceleration. Make sense? Okay, so the force that I'm putting in is, this is the force that I'm using to move the coin. The effective force is going to equal the overall force. Now that's the system. So I can convert this to Laplace domain by just capitalizing the u and the y, and the derivative y dot just becomes s capital Y, and the y dot dot becomes s squared capital Y. So this is a pretty trivial, transition to S domain. And then I want to create a transfer function for this. So in order to do that, I have to kind of rearrange the terms so I have to get the output divided by the input, right? What's the output? The output is y, the position, right? And the input is the force I want to push the coin with, right? So I have to get it into the form where I have y over s. Y over u, rather, right? Y over u. So I have to, first of all, get y, everything that's multiplied against y on one side, everything gets multiplied against u on the other side. So I'll do that. And then I will factor out y. And then what do I need? Y over u. So I need to divide both sides by u, and then divide both sides by this, right? ms squared plus bs, right? So I end up with y over u is 1 over ms squared plus bs. Make sense? Okay, and then I have to see if, well, first I want to see if the system's stable. I have to get this into a polynomial form, right? Now, the problem here is that it's s squared plus s. So I can factor out an s here, and I get s times s plus b over m. Right? So this is a polynomial already, and I just basically factor it by factoring out s. So I end up with two poles. There's two poles. One pole is s equals 0, and the other pole is s equals minus b over m. Now, that's a b over m. That's positive, right? Yeah, because the coefficient of friction and the mass will both be positive, and so, but it's going to be negative b over m. Sorry, negative b over m here, right? So that's actually a negative pole, right? That's good. That's fine. But s equals 0. That's not good enough for stability. S equals 0 means you've got a pole that's s equals 0. So that means it's actually not stable. Even a simple system like that is not stable. And so you might say, wait a minute, what do you mean? What do you mean it's not stable? If you have a coin laying on a desk, you're saying that's not a stable system? Well, it turns out it's not, because if I give it a step response, and again, what's the response here? What are we talking about? The response is force in, position out, right? If I give it a force starting at 0, and then I instantly increase the force to 1, instantaneously go from 0 to 1 force, then it'll fire that coin like a bullet, basically, and it'll shoot it like it'll shoot it. And so this is the response. You can see it's unbounded. I think this is, the problem here is it's not realistic to be able to apply this kind of force in reality, but it's still technically an unstable system. Okay, so the question is, how do we fix that? We have to create a controller, and so we'll create a closed loop controller for the system that allows me to apply a force but monitor where it is, right? And then be able to very carefully move that coin to put it on the spot I want to put it on. But we'll have to cover that next time because I just ran out of time. So I'll finish this lecture next Monday, and then after that, we'll get into our last topic, which is the real-time systems. Okay, and we have a quiz. Like I said, the quiz you have 2 weeks because the quiz covers the whole control theory stuff. All right, we'll see you in lab on Wednesday.